Chapter 6, Beyond Efficiency, a Critical Political Economy Perspective on AI Code Generators in Computing Education. Chapter Preamble. This chapter completes Aim 2 by offering a sociological critique of code-generating AI and its implications for computing education in the capitalist economy of the United States. Drawing on sociological theories of Marx and Weber, we analyzed interview data from the studies described in chapters 2 to 5 related to the area of critical political economy, CPE. This sheds light on the capitalist biases that novices will bring into their interactions with code-generating AI in their education and later careers. After considering the social hazards our data signaled about adopting AI in CS education, we suggest mitigating educational interventions, concluding Aim 2 of this dissertation. Authorship, reuse, and licensing statement. This chapter was co-authored with Claire Wood and Ellis Barnes, who consented to the inclusion of this chapter in this dissertation. This study explores a dataset that overlaps with Chapter 3, but Chapters 3 and 6 explore different research questions, and this chapter analyzes additional data. For additional information, see Authorship, Reuse, and Licensing Statement in Chapter 3. All co-authors across both chapters, Sarah L. Riggs, Claire Wood, and Ellis Barnes, provided explicit consent for the inclusion of this chapter in this dissertation. The content from this chapter may appear in a future ACM publication. The license for that paper applies to this chapter. The fallback license is listed on the copyright page for this dissertation. ACM allows complete reuse of published papers in doctoral dissertations per the following section of the ACM author rights policy, retrieved on March 16, 2026. Authors can include partial or complete papers of their own in a dissertation as long as citations and DOI pointers to the versions of record in the ACM digital library are included. Abstract. Generative AI tools such as GitHub Copilot are reshaping how novice programmers learn to code, yet their adoption raises urgent questions about the entanglement of technology, education, and capitalist values. While computing education research has largely evaluated AI code generators in terms of performance, cheating, and pedagogy, less attention has been paid to how these tools reproduce broader political economic ideals. Drawing on critical political economy, CPE, this study examines how capitalist values manifest in students' experiences with code-generating AI and the consequences of those values. We conducted interviews with 27 novice programmers at 2 U.S. universities who completed programming tasks under time pressure, with and without GitHub Copilot. We identified 3 interrelated dynamics. 1. Rationalization and automation bias, where students privileged efficiency and accuracy by deferring to AI, often at the expense of autonomy. 2. Individualism, where students assumed full responsibility for regulating, guiding, and owning AI-produced code, leading to guilt and self-blame. And 3. Alienation, where reliance on Copilot estranged students from the labor of programming and from collaborative social relationships. These findings extend sociological critiques of capitalism into CS education, highlighting how students are positioned simultaneously as consumers and producers of commodified intellectual labor. We argue that CS education must cultivate AI literacy that resists defaulting to capitalist focus on productivity and efficiency, instead encouraging critical reflection on how to use AI to promote human welfare within computing. By bridging sociology with computing education, this study offers a framework for understanding the socio-political hazards of AI in the CS educational context. 6.1 Introduction. Advancements in generative artificial intelligence, AI, have enabled a booming marketplace of artificial intelligence-driven development environments, AIDs, that help to produce and maintain computer code in revolutionary ways. Cutting-edge AIDs come with advanced user interfaces for making use of generative AI in the coding process directly within an integrated development environment, IDE, where a developer writes their code. In the early 2020s, products such as GitHub Copilot and Tab9 began offering inline completions powered by AI. Even popular generalized chatbots such as ChatGPT can act as aids, writing near-perfect code in numerous languages, planning complex software projects, and working with existing code from human developers. Following research about the benefits of chat-style interactions for coding with AI, many of the specialized aids began including the chat paradigm within their feature sets. In 2025, GitHub Copilot and other aids like it offer not only code suggestions and chatting, but also interactive editing, action taking, error detection, and AI-powered code-based search functions, to name a few. As the capabilities of AIDEs progress, they offer increasingly compelling propositions to individuals and businesses seeking to enhance their software development endeavors. In market-driven, i.e. capitalist, economies, the proposition posed is increased profitability, a concept which transfers awkwardly and inadequately into CS education. Whereas profit-seeking prioritizes producing code quickly, programming endeavors in CS education are designed to help students learn foundational skills and concepts. These two mindsets are at odds, but the conflict is far older than modern AI. To attain the capital represented by academic credentials, CS students must produce many assignments and assessments consisting of code and code-related media under time pressure ranging from minutes to years. Thus, the structure of curriculum is itself a representation of the market-driven values in which the U.S. education system is steeped. Aids complicate this environment by doubling down on the capitalist obsession with productivity and likening the goals of a profit-driven entity to that of every individual themselves. Whereas a sole proprietor producing code for the software marketplace might find such tools as Copilot, being designed with productivity in mind, as being well aligned with their needs and intentions, the typical CS student might not. Worse yet, the emphasis of the educational system on productivity of educational deliverables means that CS students are being invited by AI vendors to exploit the productivity-enhancing effects of aids rather than exploring their potential learning benefits. Discussion about the comparative risks and benefits of aids for CS students' learning is lively. Early work frightened the CS education community by demonstrating that aids were rivaling the abilities of CS students on educational deliverables. Despite fears students would soon begin using AI to cheat on their CS assignments, scholars have also considered that AI can help students to better understand coding concepts, remove barriers to succeeding in computer science, and unlock new teaching capacities for busy instructors. Although aids offer legitimate enhancements to traditional modes of learning, teaching, and practicing CS, their current posture in the economic landscape makes them uniquely threatening to CS students learning to code at the start of this new era. Traditional sociological critiques of the CS education system have focused extensively on how it reproduces power structures over time. These draw heavily on the work of Bourdieu and suggest that the omnipresent challenge of diversifying participation in CS owes its roots to nuanced systems of capital. Though such approaches promote resisting unjust power structures, they are limited in that they avoid critiquing capitalist economic values. Properly investigating the implications of AI for CS education requires scrutinizing its entanglement with market-driven economics. To this end, the goal of this article is to explore and critique capitalist values that code-generating AI reinforces within CS education. While sociological theory has been widely applied to study labor, technology, and education, it has rarely been integrated fully into engineering and CS education research. Critical political economy (CPE) frameworks offer concepts such as alienation, rationalization, and commodification that illuminate how capitalist logics shape both labor and learning. Yet, in CS education, sociological perspectives are most often limited to individual-level analyses of cultural or social capital, typically in service of diversity and participation goals. What is missing is sustained engagement with the theories that interrogate how institutions like education mirror and reproduce capitalist values, and what consequences follow from these arrangements. Critiquing capitalism is not new to sociology. It has long been central to the discipline and continues to be a vital point of engagement. From Marx's analysis of alienation and Weber's theory of rationalization, sociologists have used such frameworks to examine how capitalist systems shape our society. More recent work extends these logics through credentialism, bureaucratic organization, and the commodification of knowledge. Similarly, scholarship on technology has demonstrated how machines and digital systems function not as neutral tools, but as vehicles for capitalist control, efficiency, and de-skilling. Our contribution builds on this tradition by applying these sociological critiques to computer science education and the adoption of AI code generators. In doing so, we show how capitalist values embedded in technology and education intersect in CS classrooms, shaping novice programmers' experiences and raising new questions about labor, learning, and autonomy in the age of AI. In the educational context, we reveal how students are positioned not only as consumers of knowledge, but also as producers of exchange value, where their intellectual labor is commodified. This paper bridges the gap between sociology and CS education by bringing Marxist and Weberian frameworks into dialogue with empirical CS education research. This study contributes a novel critical framing of code-generating AI in U.S. CS education using interviews from 27 novice programmers at 2 universities who programmed under time pressure with and without the GitHub Copilot aid. Through a systematic qualitative analysis process, we mapped out an interconnected set of capitalist values present in participants' reflections on programming with Copilot compared to programming alone. By doing so, we move beyond describing student outcomes to explaining how capitalist economic values structure novice programmers' encounters with AI code generators. Research question: how can novice programmers' thoughts and feelings about using GitHub Copilot to code be explained by the entanglement of the United States computer science education system with capitalist economic values? 6.2 Theoretical Framework. 6.2.1 Critical Political Economy. Critical political economy, CPE, is a theoretical approach that interrogates how money, politics, and power shape and control resources according to dominant ideologies and power structures. Originating from classical political economy in the works of scholars like Adam Smith, David Ricardo, and Karl Marx, CPE examines how capitalism organizes social relations, shapes power dynamics, and influences technological interactions and labor processes. More specifically, it is rooted in Marxist analyses that critique capitalism not just as an economic structure, but as social totality. Marx focuses on the value of labor, how people can feel disconnected or, quote, alienated from their work, and how capitalists gain profit from the labor of workers. These ideas help explain how capitalist systems create and maintain patterns of wealth and power. Marx's contributions remain central to CPE, especially his exploration of commodification and alienation. Commodification is the abstraction of a product's unique value for people, i.e., quote, use value, end quote, to quantifiable, quote, exchange value, end quote, suitable for commerce. Alienation refers to the estrangement workers experience from their labor, the final product of their labor, their fellow workers, and ultimately themselves through the extraction of their labor as a resource by those who own the means of production. Specifically, Marx says, quote, the alienation of the worker in his product means not only that his labor becomes an object, an external existence, but that it exists outside him, independently, as something alien to him, and that it becomes a power on its own confronting him. It means that the life which he has conferred on the object confronts him as something hostile and alien, end quote. An example of this concept is found in Braverman's analysis of factory labor, where increased mechanization and managerial control resulted in workers losing autonomy, feeling reduced to mere operators of machines rather than skilled artisans. This condition intensifies as workers become subordinate to technology, increasingly operating as mere appendages of machines rather than as autonomous creators. Marx's theoretical framework identifies 4 distinct forms of alienation: alienation from products, labor processes, self, and social relations, each created because of capitalism. More recent scholarship argues that alienation should not be viewed as merely individual feelings of dissatisfaction. Instead, alienation is a systemic and objective condition arising directly from the division of labor within capitalism. In this framework, alienation occurs when workers are separated from the products of their labor, which are appropriated, commodified, and ultimately used to limit their autonomy. Additionally, contemporary forms of alienation are not confined to the factory floor, but extend into cognitive and affective domains, where creativity and emotional labor are commodified. This process creates a paradox where society appears to become more connected and interdependent, yet individuals feel increasingly isolated and powerless due to the control and impersonal nature of capitalism. Additionally, in Marx's critique of capitalism, there is a distinction between use value and exchange value. Use value refers to the practical utility of a commodity, the capacity of an object or service to satisfy a human need. Exchange value, by contrast, reflects the commodity's worth in the marketplace, expressed in its relation to other commodities or monetary terms. While use value anchors commodities in concrete human needs, exchange value abstracts them into quantifiable units of comparison, enabling their circulation as capital. Commodification occurs when the unique qualitative dimensions of use are subordinated to the quantitative logic of exchange. such that the social relation between producers and consumers appears as a relation between things. This tension between use and exchange is at the heart of CPE analyses, revealing how capitalist systems prioritize profitability and accumulation over human need, and how institutions, including education, reproduce these dynamics by treating knowledge and skills as commodities whose exchange value outweighs their use value. 6.2.2 Rationalization. Alongside Marx, Max Weber's theory of rationalization provides additional explanatory power when considering the impact of artificial intelligence within computer science education. In The Protestant Ethic in the Spirit of Capitalism, Weber explains the shift between traditional ways of life and the industrialized modern world. Analyzing the content of discourse on labor prior to the Industrial Revolution, he describes how Protestant workers equated economic success with divine favor, subsequently embedding the values of efficiency and wealth accumulation within work. As a result, over time, the traditional and religious customs that informed labor gave way to reason, logic, and science, with work being valued for its economic benefits rather than for tradition or passion. For Weber, this shift, what he calls rationalization, reflects a preference for efficiency that now defines modern society. This leads to what is known as instrumental rationality, the idea that human activity should primarily serve practical, goal-oriented ends. Bureaucracy is one institutional form of this mindset, in which organizations are divided into specialized units to maximize efficiency and productivity. More than a structural description, Weber viewed bureaucracy critically. Its emphasis on standardized procedures ensures smooth operation for economic gain, but also subjects people to domination, limiting autonomy and stifling creativity. Building on this, bureaucracy can be understood as a mechanism of control rooted in knowledge. By standardizing labor, it assigns individuals to predefined roles and strict procedures, aiming to minimize variation in outcomes by privileging the most efficient means of generating economic gain. This makes instrumental rationality the dominant framework for all decision-making, replacing moral and communal bonds with competitive, individualistic structures. Weber argues that this is an irrational system of governance where the pursuit of efficiency leads to a restrictive and alienating social order. Weber's theory of rationalization rests on an interpretive approach that examines how individuals make sense of their actions. While this may appear psychological in nature, it is fundamentally sociological. The emphasis is not on isolated mental states, but on how orientations toward action reflect broader social structures, values, and norms. In this sense, analyzing individual meaning-making reveals how cultural expectations and institutional arrangements shape thought and behavior. This sociological perspective provides a useful foundation for our study, as it highlights how students' experiences with AI are embedded in and shaped by capitalist systems. 6.2.3 Technology. Marx saw technology not as inherently liberating or oppressive, but as a force shaped by the social and economic context in which it is developed and employed. In capitalist societies, he argued that technological advancements are typically used not to reduce human suffering or labor, but to increase profits and control over workers. Machines and tools become instruments of alienation when they are used to de-skill labor, speed up production, and maximize surplus value for the capitalist class. Braverman identifies two fundamentally different perspectives on technology. The first is the engineering perspective, which understands technology primarily through its internal functions, defining machines by their technical characteristics. The second is the social perspective, which emphasizes technology's relationship to human beings and defines machines according to their connection to human labor. Within capitalism, the social perspective dominates. Technologies are designed and implemented to extract value and maintain control over workers and their products. This tendency reflects what Ritzer terms McDonaldization, a contemporary iteration of Weber's theory of rationalization. Within McDonaldization, modern institutions, for example, travel, retail, education, etc., operate according to the same principles as the fast food industry: efficiency, calculability, predictability, and control through non-human technology. These principles standardize processes to deliver predictable outcomes for profit maximization. Control through non-human technology, the final tenet of McDonaldization, is central to this logic. With increasing digitalization, more tasks are automated under the premise that machines reduce variability and error. Digital kiosks replace cashiers, turning customers into unpaid laborers for corporations. In manufacturing, the industrial internet embeds sensors, trackers, and chips into machinery so that production components communicate autonomously, bypassing the need for direct worker or managerial oversight. Modern information technologies are celebrated as accelerants of innovation, competition, and economic gain for tech companies. Human laborers become valued more for their ability to operate interfaces and follow protocols than for their capacity to generate original solutions. The consequences of widespread technological adoption extend beyond reducing human autonomy. They also transform how laborers relate to their work. Automation bias describes the tendency to over-rely on automated cues as substitutes for the cognitive effort of seeking and processing information. This bias often manifests as a preference for suggestions generated by technology, even if those suggestions conflict with other available information. Research shows that excessive dependence on automation, commonly used to manage repetitive and monotonous tasks, can foster complacency, degrade skills, and erode situational awareness. The rise of AI in the modern world is not an exception to this trend, but an extension of it. The use of AI in coding represents a form of attentional integration within digital labor that may discourage programmers from relying on their own skills in favor of the convenience AI provides. For computing educators, adopting a critical lens is essential for understanding how the tools they create operate within broader political economic systems. Ultimately, technology under capitalism is less of a neutral instrument than a conduit of profit and control. From Marx's analysis of machines as instruments of alienation to Braverman's social perspective on technology, technological design has long served capital rather than labor. Contemporary forms, i.e. McDonaldization, extend this logic and illustrate how efficiency and predictability are achieved by reducing worker autonomy and creativity. AI and automation bias mark the newest turn in this trajectory, drawing workers into patterns of dependence that subtly reshape how they engage with their own labor. 6.2.4 Education. Marx imagined capital as a tangible means of production, but modern scholars argue that our current economy is driven by intangible capital. Intangible capital refers to non-physical assets that generate value, such as knowledge, intellectual property, algorithms, etc. Unlike tangible capital, factories, machines, or raw materials, intangible capital assets are not material objects, but forms of knowledge and innovation that can be leveraged for economic gain. In contemporary capitalism, these assets underpin value creation, shifting the focus from physical production toward cognitive, informational, and cultural resources. Education under capitalism often mirrors broader economic structures, reinforcing the systemic inequalities central to capitalist production. Contemporary education is increasingly shaped by intangible capital, such as knowledge, skills, and credentials. These intangible assets are treated as forms of capital investment, expected to yield future economic returns for both individuals and institutions. This framing repositions students not just as learners, but as future capital holders and entrepreneurs of the self, whose value is tied to their ability to accumulate and mobilize intangible capital in competitive markets. Pierre Bourdieu's concept of cultural capital further clarifies this dynamic. Cultural capital refers to non-economic resources such as educational qualifications, knowledge, and social behaviors that confer status and advantage in society. In educational contexts, cultural capital is often aligned with intangible capital, influencing students' ability to successfully navigate and exploit educational systems and labor markets. He argues that educational institutions serve to legitimize and reproduce existing social hierarchies by rewarding students who possess certain forms of cultural capital, thereby perpetuating inequalities and reinforcing capitalist class structures. Henry A. Giroux is a central figure in critical pedagogy and one of the most influential voices applying critical political economy to the analysis of education. His work challenges how neoliberalism transforms educational institutions from spaces designed to foster democratic engagement into systems oriented around market logic and private gain. In Neoliberalism's War on Higher Education, Giroux explains that universities are increasingly structured like corporations. Students are treated as consumers, faculty as managed labor, and knowledge as a commodity for sale. He critiques the erosion of public funding and the growing influence of private capital, which results in universities prioritizing job training and economic output over critical inquiry and civic responsibility. In the capitalist education system, students are simultaneously framed as both consumers and producers of value. The educational system, particularly in neoliberal contexts, is structured to reproduce labor power attuned to the needs of capital. This includes the emphasis on STEM over the humanities, the rise of credentialism, and the privatization of educational services. Structurally, education reflects broader capitalist dynamics through its bureaucratic organization. For nearly 2 centuries, bureaucracy has shaped educational institutions, characterized by extensive administration. Such bureaucracy imposes significant structuration within academia, with disciplinary divisions controlling the types of knowledge produced and promoted by different departments. Consequently, this fosters intense competition over specialized forms of knowledge, positioning universities as hyper-specialized bureaucratic entities deeply involved in knowledge production and mediation. Similarly, standardized course loads for students perpetuate intellectualism as a profit-making device as the value in higher education shifts from the quality of knowledge one can obtain to how effectively the university can produce individuals ready for the workforce. One could argue that vocational qualifications secure a level of quality in knowledge generated and mediated to students, but even these represent bureaucratic standards that are in place to ensure homogenized operations. These perspectives illustrate how education functions as a critical site in the political economy of capitalism. The rise of intangible capital has reframed knowledge, skills, and credentials as investments, while cultural capital shapes who benefits from these processes and who is excluded. Under neoliberalism, universities increasingly mirror corporate logics, commodifying knowledge and redefining students as both consumers and producers of value. Bureaucratic structures further entrench these dynamics, standardizing knowledge and aligning educational outputs with the demands of capital. In this way, education not only reflects broader economic transformations, but actively reproduces them, reinforcing inequalities while legitimizing the capitalist order. 6.3 Related work. 6.3.1 Social theory in CS education. The use of sociological theory in CS education research is mostly limited to promoting diversity by considering capital at the individual level. A popular foundation is Bourdieu's theory of cultural reproduction, which is built on his understandings of capital, its embodiment in individuals, habitus, and its location of use, field. In addition to economic capital, i.e. capital and property, Bourdieu emphasizes cultural and social capital, where credentials and relationships are also assets. CS education research focuses on interventions that promote participation from underrepresented students by helping them attain and recognize cultural and social capital. Another branch of research attempts to resist hegemony using pedagogies that encourage students to reshape the dominant culture within their education. However, there is limited work that critiques the CS education system using sociological theories about capitalist economies. 6.3.2 AI in CS education. Artificial intelligence-driven development environments, AIDs, i.e. AI code generators, such as ChatGPT and GitHub Copilot, offer new ways to assist computer science students with programming and related tasks. In the past, CS students sought help from social resources like peers, instructors, online communication, and non-social resources like courses, books, and online information. AI is an asset for CS education, but also introduces ethical and other challenges such as over-reliance and influences on students' coding habits. CS instructors are learning to cope with AI, but are not fully aligned with students regarding appropriate policies. Tools such as Code Help can provide AI assistance to CS students without generating code, but code-generating AI nevertheless remains widely available to students. 6.3.3 Performance and learning effects. Though aids improve novices' programming performance, their benefits for learning outcomes are not yet clear. Early work was inconclusive about the performance benefits of aids for programmers in general, but more recent evidence has solidified that aids improve novices' programming performance. Although efficiency potentially allows students to cover material more quickly, what matters more in educational context is whether students are meeting learning objectives. AI-inclusive CS pedagogies have begun to win the appreciation of students and instructors alike. Unfortunately, aids have not been found to significantly impact learning outcomes overall. Aids only seem to improve learning when used in certain ways, highlighting the general inconsistency of AI's impacts. The research is mixed about how CS students choose to use AI when they are allowed. Some use it to outsource critical thinking, while others use it as a supplement. A study of 32 CS students found that using AI more for critical thinking tasks, code generation and debugging, was significantly correlated to worse learning outcomes. This aligns with the findings of reference 34 that friction between AI outputs and CS students' preconceived ideas is a catalyst for meaningful engagement with the subject matter. To reach a point of friction, the student needs to have put forth sufficient thought about a programming task to have a basis for comparison. In this vein, Kazemadabar found that young CS learners, N equals 33, who used AI for some but not all work, showed a non-significant trend toward better learning outcomes compared to full insourcers or outsourcers. Overall, whether AI is beneficial for learning computer science seems to be highly variable according to different circumstances and choices. 6.3.4 Social Effects. By mimicking human assistants, aids present a threat to social learning in CS. Existing approaches such as student pair programming are beneficial to students' well-being and performance. Aids are an avenue for programmers to avoid social help seeking. Within pseudo-social AI interactions, students can attain their primary objectives without the undesirable properties of socializing with humans. For example, CS students find that AI offers less judgment compared to peers or instructors. Furthermore, programmers often see aids as CS experts, meaning they expect superior assistance from AI as compared to, for example, a peer. Once programmers begin to go for AI help, they tend to stray away from other resources. This transition reflects the theory of rationalization. The obsession of students to achieve academic performance metrics causes them to devalue social connections within the context of learning to code. 6.3.5 Self-efficacy effects. Student self-efficacy, which is a strong positive predictor of academic performance, can potentially be boosted by aid use. One study, N equals 45, has shown that using AI in a CS course provides significant benefits to self-efficacy and motivation. However, in another study of CS students, earlier and more frequent AI use was conversely associated with low self-efficacy and course grades. In empirical studies, programmers using AI tend to blame themselves for negative outcomes rather than blaming the AI, yet do not always take credit for AI performance gains. A possible reconciliation of these findings is that struggling students with low baseline self-efficacy seek AI assistance early and often, leading them to gain a false sense of competence. When the programmer's true competence is more transparent, as in reference 18, self-efficacy is less likely to improve as a result of AI assistance. 6.3.6 Autonomy Effects. Aids reduce CS students' autonomy. In empirical studies, programmers report desiring to maintain control over aids while programming, but this is not often borne out in reality. For example, several studies have found that programmers heavily modify their work processes in response to the presence of AI. Aids can also be intrusive and can cause novices to lose track of their progress within a programming task. As mentioned earlier, the resulting, quote, illusion of progress, end quote, can cause a false sense of programming competence. Loss of autonomy is especially likely when a CS student lacks knowledge on the subject at hand. A study in a CS course, N equals 56, had students take assessments with ChatGPT prior to learning the relevant course material. Though students were capable of achieving correct answers, their incorrect answers indicated they were easily misled due to lacking the necessary knowledge to identify bad advice. In an economy that is already heavily bureaucratized and siloed, losing autonomy over programming further alienates programmers from the larger societal benefits of their everyday work. 6.3.7 Inequality Effects. Aids are likely to worsen existing inequality in CS education. Several studies support that AI is more useful to stronger CS students than weaker ones. AI access is another source of inequality. As of 2024, internet resources still dominated AI for CS students seeking help. But among aids, ChatGPT dominated GitHub Copilot, though the latter is designed more specifically for programming. That is, students are using the most accessible resources, not necessarily the most effective ones. In the past, disparities in access to the internet reinforced existing economic inequalities. Since AI-inclusive pedagogy is new, It will also likely cause widened educational inequality between more and less resourced institutions according to who can afford to invest in it. Many studies have shown that effective shepherding of AIDEs is key to their effectiveness. The long-term effects of these factors are not yet clear, but evidence for inequality is already surfacing. At least 2 studies have found that student use of AI code generators is bimodally distributed among students who are familiar with them. Unless CS education deliberately combats these effects, what is likely to follow is a, quote, Matthew effect, end quote, whereby students' existing advantages reinforce themselves. 6.4 Method. 6.4.1 Participants and Context. The data were collected alongside a controlled laboratory experiment comparing various subjective and objective measures between solo and AI-assisted programming conditions. 2 cohorts of participants were recruited at 2 public research universities in the same U.S. state, a predominantly white institution, PWI, and a historically black university, HBCU. Participants were recruited by convenience, taking volunteers from introductory programming courses. Ethical approval was obtained for both studies, and all participants provided informed consent and were paid for their time. Interested volunteers participated in the study outside of class, and no volunteers were turned away. PWI cohort. The PWI cohort included 17 students from an introductory CS1 course taught in Python who identified as mostly female, 11 female, 5 male, 1 unknown, and Asian, 8 Asian, 3 Asian and white, 4 white, 1 Latinx and black, 1 Latinx and white. A recruitment announcement was made in 2 of 3 sections of the CS1 course to a total of roughly 500 students in spring 2023 when data were collected. HBCU cohort. The HBCU cohort included a gender-balanced sample, 5 female, 5 male, of only black students from a CS2 course taught in Java that immediately followed the Python CS1 course. Based on comparing the syllabi for the CS1 courses at both universities, recruiting from the CS2 course ensured the most similarity between the ability levels of the 2 cohorts. The recruitment announcement was made to all 5 sections of the CS2 course to a total of roughly 100 students in the spring 2024, when data were collected. Experimental context. The qualitative data in the present study comes from interviews conducted following participants' completion of a controlled programming experiment. Note that the focus of the present study is on what participants' reflections on their programming experiences say about AI's role in reinforcing capitalist values in CS education. As such, the details of the programming experiment are not the major contribution here, but we provide them for necessary context. Programming tasks. Tasks were selected from the Human Eval dataset, which is used to evaluate LLM's coding abilities. It is intentionally published in a compressed format to mitigate its inclusion in training data. Despite efforts to exclude it during training, the open source nature of Human Eval means GitHub Copilot may unintentionally be trained on some of its tasks. All tasks provide a prompt, typically with example inputs and outputs, and expect a Python function to return an output based on input parameters. Each task comes with a set of test cases to check a solution's correctness. An example task, ID equals 104, includes the following prompt. Quote, given a list of positive integers x, return a sorted list of all elements that hasn't any even digit. End quote. To avoid this article contributing to benchmark pollution, we will not provide any solutions to Human Eval tasks. 9 teaching staff from the CS1 course at the PWI helped to examine and select tasks of tractable but varied difficulty to use in the study from the Human Eval dataset. Using the consensus of multiple raters, 4 sequences of tasks from Human Eval were constructed to have easier tasks toward the front, harder tasks in the middle, and tasks requiring special knowledge like math formulas at the end. The goal was for all sequences to have similar difficulty profiles to one another without participants getting stuck early. Participants were required to work on tasks one by one so that time management did not confound the results. To move to the next task in each sequence, participants had to pass all of the current tasks' unit tests, which are provided within Human Eval. The task sequences by task ID were 24, 3, 0, 12, 26, 37, 51, 49, 53, 52, 18, 69, 25, 70, 7, 2, 23, 74, 14, 9, 6, 161, 19, 22, and 35, 67, 72, 5, 13, 38, 20, 45. AI is poised to perform better on human eval tasks than real-world programming tasks, but the main reason for this is their simplicity. This will be an issue for any task that is simple enough for a novice to attempt. Anecdotally, both teaching staff and participants agreed that the selected human eval tasks closely mimicked the types of tasks that would be typical for programming assignments and timed assessments in a Python CS1 course. Programming setup. Participants programmed in Python on Apple iMac computers using Visual Studio VS Code. A custom VS Code extension provided a button to control the task progression. A first press began the 8-task sequence and started a 20-minute timer. This placed all human eval instructions for the first task in a PDF file on the right side of a split screen and opened a Python file on the left. The Python file contained an empty function to implement, stripped of all comments and instructions. This prevented Copilot from ingesting the task prompt unless the participant explicitly introduced it from the PDF via comments or chat messages. A Python testing and running interface was provided by the standard Python extension for VS Code, and a terminal was available for running and testing too. The unit tests came directly from the human eval dataset and could be seen but not changed by participants. After implementing testing and running the code ad libitum, the study control button would allow them to advance to the next task if their implementation passed all tests. Otherwise, they could not advance. Upon expiration of the timer, the code was automatically submitted and evaluated as is. While the first cohort was not allowed to use internet resources at all, the second cohort was allowed to do so in both AI and solo conditions on the advice of our peers in the CS education community. This trade-off sacrificed exact methodological parity for increased ecological validity. The GitHub Copilot VS Code extension was available when participants worked with the AI, while the Python extension provided standard symbolic autocomplete for solo programming. Copilot is a popular mainstream code-generating AI assistant that is free for students and teachers. Because GitHub Copilot is constantly being evolved and updated, the version used by the second cohort was slightly different than for the first. Both cohorts had inline suggestions for code within their editor and the ability to invoke a panel of multiple completion options following their cursor position. However, the HBCU cohort also had chat features and context direction tools available. Again, it is important to note that Copilot could not read the task prompts from the PDF instruction files. Programming procedure. Participants provided informed consent before training extensively on GitHub Copilot and the experimental setup. They then programmed for 4 20-minute bouts corresponding to each of the 4 task sequences, using GitHub Copilot for 2 bouts and working alone for 2 more. The ordering of the task sequences and the assignment of AI treatments was counterbalanced across participants, with the 10 HBCU participants' task lineups mirroring 10 of those from the PWI. Participants were incentivized by 2 $10 bonuses offered within each cohort, 4 total, to complete as many tasks as possible, using the AI as much or as little as needed. They were scored based on how many total tasks for which they passed all unit tests over all programming bouts. Interview procedure. Semi-structured interviews were conducted using the 5-phase approach described in Chapter 7 of Reference 4. This format eases participants into and out of the main topics of interest and avoids ambiguity and bias by asking open-ended questions and following up on markers of key experiences and sentiments. One author performed all 27 interviews. The goal of the interview was to explore the subjective experience of programming with Copilot under time pressure and its impacts on participants' thoughts and feelings. Member checking was performed frequently throughout all interviews to facilitate valid interpretations during analysis. However, it was not feasible to perform post-hoc member checking with participants for the findings presented here. Interviews were audio recorded and transcribed using automated transcriptions, with revisions made manually by a trained researcher. 6.4.2 Data Analysis. During an initial review of the interview transcripts from the 17 participants at the PWI, one of the authors noticed a pattern that many participants' comments alluded to underlying capitalist values. This inspired us to undertake a deductive qualitative investigation focused specifically on classifying, explaining, and critiquing these patterns. To do so, 3 trained qualitative researchers analyzed the data in 4 phases, beginning with a deductive approach in phases 1 and 2 and moving to an inductive approach for phases 3 and 4. Phase 1, quote selection. In the first phase, 1 researcher independently reviewed each interview transcript, identifying quotes related to the research questions. The second researcher reviewed each transcript and could add new quotes, but was not permitted to remove any previously selected quotes. This ensured a comprehensive selection of quotes that could later be refined for relevance. The researchers followed the broad rule, quote, select any quotes possibly reflecting or resisting capitalist economic values, end quote. Including duplicates, this phase yielded 190 quotes from the HBCU and 611 from the PWI for a total of 801. Phase 2, quote pruning. In the second phase, 2 researchers independently reviewed all quotes from phase 1, flagging any that seemed irrelevant to the research questions. We used a crossover strategy, so each of the 3 authors covered 2/3 of the data and overlapped by 1/3 with each of the other authors. The shared instruction was, quote, flag any quotes that do not relate to capitalist values or do not reflect an idea or experience of the participant's own. For example, I don't think X, but some people might, end quote. For each flagged quote, the selector and the flagger met to resolve the disagreement and decide whether to keep or discard the quote. This reduced the total dataset to 397 quotes. Phase 3, initial coding. In the third phase, 2 researchers independently coded each quote from phase 2 using an inductive approach and the same crossover strategy. While the quotes were identified through a deductive process, coding remained inductive. There were no predetermined limits on which capitalist values might be relevant. The shared guideline was, quote, label and describe the relevant capitalist values reflected or resisted by the quote, end quote. Phase 4, codebook, synthesis, and refinement. In the fourth phase, all 3 authors met to merge all codebooks and reevaluate any quotes irrelevant to the research question. We reviewed each code, combined similar codes, clarified descriptions, subcategorized codes under others as needed, and eliminated some. Each decision was discussed and approved by at least 2 of the 3 researchers in the case of disagreements. Finally, we checked that each code was internally coherent, distinct from others, and grounded in the data. Each theme was supported with representative quotes and revisited in relation to the research question to confirm relevance. The resulting themes are discussed in the next section. In total, the final dataset included 217 quotes, of which roughly 5% are reported below. 6.5 Results. Participants' quotes revealed 4 main themes reflecting capitalist values in relation to programming with code-generating AI. First, they reflected an automation bias that encouraged them to use Copilot rather than engage with programming tasks. Second, they promoted individualism by projecting all aspects of interacting with it onto a reflection of themselves. Third, they demonstrated Copilot's alienation of the programmer from the programming process and social opportunities. Fourth, they revealed the underlying tendency of rationalization, i.e. prioritizing efficiency and other measurable outcomes that explain the observed automation bias. 6.5.1 Automation Bias. Nearly all participants reported applying an automation bias while coding with Copilot. Merely using Copilot was not considered here. Instead, quotes specifically related to using Copilot as an alternative to manually engaging with a task. This included the main purpose for this bias, pragmatism, its expression as passivity, and its consequence, temptation. Pragmatism. Pragmatism is the belief that using Copilot is more efficient for coding than not using it. The study design attempted not to enforce this belief, as participants were taught both benefits and drawbacks of Copilot in training and instructed to use it only as much or as little as needed to score as highly as possible. Therefore, their preference to use Copilot over engaging with a task reflected a bias, whether pre-existing or discovered, that using this automation would be better than not. They described how it saves time, makes coding more efficient, and helps get things done because it has the answers they need. For example, participant J24 began by trying to collaborate with Copilot, but realized pasting the entire task description into the chat panel was more successful. Similarly, participant I47 found that even when they did not need Copilot, they were better off with taking its suggestions. Quote, "At first I started asking it to explain because I was trying to, figure it out, but the best strategy was just to copy and paste." End quote. J24. Quote, "I think this is one of the ones where if I had more time, I definitely didn't need Copilot, but the ease of Copilot made it more like learning to just go with what Copilot had generated because it would be correct." End quote. I-47. Participants understood that, like in the study, efficiency would often be a primary goal in their future coding endeavors. For example, participants J11, J16, and J20 said they would use Copilot when they just needed to get something done for school, potentially revisiting the work later. Participant J13 emphasized that this approach would be inappropriate for school, but would be acceptable in the workplace, where productivity is the main goal. Generally, all agreed that when productivity or efficiency is a priority, using an AI code generator is obviously preferable to completing a task alone. This likely reflects the reality that they were more productive with Copilot than without, but could also be influenced by a general bias to believe automation is superior to manual work. Passivity. Passivity is the act or mode of deferring to the advice of Copilot over one's own thoughts, i.e. the manifestation of participants' automation biases. For example, participant I-16 said that they sometimes gave Copilot complete control, while I-19 explained how it felt to take a passive role with Copilot. In some cases, quote, "Copilot just solved the problem for me, and I didn't do anything," end quote, J16. The difference isn't huge, but, quote, "it's less mental taxation on you, so you're more calm," end quote, I-19. In many cases, passivity was an intentional or voluntary decision to avoid a traditional way to solve a problem and opt for Copilot's advice instead. For participant J4, they chose not to think about a problem when Copilot could do it for them. For J13, they regretfully recalled choosing Copilot over Google search. Quote, "I just asked the AI on this one, and it also gave me the answer and it was correct, so I just moved on. I did not really think about it too much. I just trusted the AI." End quote, J4. Quote, "Once I started using Copilot, I stopped using Google. So maybe for that task, I could have consulted Google to see exactly what's the problem and not relying solely on me going back and forth with Copilot." End quote, J13. On the other hand, Copilot's automatic suggestions meant participants were often forced into an involuntary state of passivity, compared to the prompt response model of Copilot's chat or popular apps like ChatGPT. Unprompted suggestions in the editor encourage users to take a back seat. Participant J20 explained the difference. Quote, "With ChatGPT, you have to kind of do a little bit of it by yourself before you can input it, but with Copilot, it's spoon-feeding you." End quote, J20. When Copilot offers its suggestion, any thought process a user has begun is hijacked by the new information. Quote, "Your eyes are sort of betraying you," end quote, when Copilot suggestions appear, quote, "before you can think," end quote, I-47. Users are forced to adapt to the direction Copilot takes them, which can be frustrating and disorienting, as noted by participants I-42 and J15. Quote, "I got sucked into the past that didn't work, and then I was stuck there, I found it difficult to get out of that hole," end quote, I-42. Quote, "It was constantly affecting my bias. It was just suggesting things that were not useful. Being in line, it changes your bias and just makes you stumble over and over and over again." End quote, J15. A takeaway is that the user interface for an AI code generator has a clear impact on the power of automation bias. When relying on Copilot required deliberate action, such as sending a prompt, passivity was a result of a voluntary choice to prefer Copilot's help. However, the involuntary side of passivity showed that preferring one's own ideas was much more difficult when Copilot preluded their thoughts. Temptation. Temptation is a durable effect of automation bias, where users struggle not to use Copilot after knowing or experiencing its practical benefit. Copilot has a way of imprinting on a user such that they become frequently distracted by considering the opportunity cost of coding alone, as in the case of participant J20. Quote, "Even if I decided I was going to ignore Copilot, while going with my own approach, I was still thinking about the possibility of using Copilot, like the opportunity cost." End quote, J20. Participants also described temptation as the alluring pleasantry associated with using Copilot to avoid work or discomfort. For example, participant J1 felt more secure working with Copilot, and I9 expected Copilot to discourage them from bothering to remember common library functions. Quote, "When I have AI, it feels like more security, like whether it's right or wrong, I could check it, or AI can help me get it right." End quote, J1. Say, quote, "I forgot what this function is, but it's okay because I know Copilot will probably be able to help me out as long as I remember at least part of it." End quote, I9. The memory of Copilot and its utility is not easily forgotten, leading to an experienced participant I13 described as, quote, "My heart says yes, but my mind says no," end quote. That is, even when a user wants to solve a problem themselves, they're drawn to prefer Copilot anyway. 6.5.2 Individualism. Individualism is the spirit that Copilot's users, rather than Copilot or its producers, should be culpable and accountable for their use of it. Participants believed that it was an individual's responsibility to self-regulate their use of AI, control it effectively, and take personal accountability for the code produced. As a result, they felt guilty for using Copilot, and when the interaction was unsuccessful, they blamed themselves. Responsibilities. The primary sign of individualism in participants' accounts was their identification of moral responsibilities related to using Copilot. First, the responsibility of self-regulation is to decide when and how much to use AI. Second, the responsibility of shepherding, see reference 59, is to effectively understand a problem and coerce AI to be useful. Third, the responsibility of ownership is to be accountable for the code produced as well as an understanding of how that code works. The responsibility of self-regulation implies that there can be a wrong time, a, quote, too much, end quote, I19, or a too little associated with using AI. For example, participant I47 said a beginner should avoid using Copilot since they would not be prepared to intervene if something were to go wrong. In other cases, participants simply stated that Copilot could have a positive impact on their learning or productivity, but only when used properly, with the proper manner being ill-defined and ambiguous. Participant I11 planned to stay away from AI more after the study, opting to work alone and only use Copilot very sparingly. Their implication is that using Copilot for too much of a project is problematic. Quote, "Trying to do it by myself as long as I can would be better, but if I need a suggestion, one little suggestion, not the whole project, that could be helpful." End quote. 11. The responsibility of shepherding says the user has a duty to effectively understand a problem and communicate their intentions to Copilot. This sentiment was that Copilot does not owe the user a seamless experience, but rather they must lead the effort. For example, participant I12 explained that identifying their intention was a key step to succeeding with Copilot. Quote, "There were some tasks where I didn't fully understand the question, and if I don't understand the question, then I don't know what I want, so Copilot can't know what I want." End quote. I12. The responsibility of ownership attaches a user to the code they produced with Copilot, such that they must be able to understand its design and answer for its behavior. Participant I5 captures both of these aspects, saying that they must understand the code and act as an authority on the work for future inquiries. Quote, "I want to be the authority on my own work, and I want to understand it. So if it's only affecting me, then I could control kind of how that's going to play out. But if I were to ever have someone ask me about it or I need to modify something, I'd want to be able to fully understand what I had submitted." End quote. I5. This quote also suggests that future consequences or retribution motivates why to understand code even when Copilot can produce it correctly. Because one's code can affect others, someone might interrogate a piece of code as a reflection of the user who oversaw its production. The user also wants to help their future self by investing in an understanding of code now so that it's easier to revisit or maintain in the future. The responsibilities of self-regulation, shepherding, and ownership span the full life cycle of Copilot's involvement, capturing the spirit of individualism within programming. A contrasting mindset would be collectivist, meaning other team members, AI vendors, or the AI itself might be expected to share the effort of producing code responsibly. However, it seems that participants believe the individual is ultimately responsible instead. Guilt and self-blaming. The sense of responsibility also led participants to have negative feelings and reflections toward themselves. Even though they were allowed to use Copilot as much as they wanted, they felt guilt for taking its suggestions to avoid work. Participant J4 described the feeling of taking Copilot's suggestions as, quote, happily guilty, end quote, going so far as to thwart their chances of earning a performance bonus by deliberately wasting time. Quote, I was really wasting time because I was feeling guilty for putting all the questions in AI and just submitting like that. So I was trying to take my time and see if I can understand it on my own, end quote, J4. Others also judged their own use of Copilot as excessive or immoral, noting, for example, how their professors might react if they were to witness their choices. Participants also engaged in self-blaming when they faced challenges using Copilot. As in the case of participant J16, they were quick to shift the blame away from Copilot itself. Quote, my understanding of this problem was kind of skewed. I think Copilot tried to the best of its ability, but I gave the instructions and that was more on me than on Copilot itself, end quote, J16. Copilot often failed to meet participants' needs, but they tended to take on the fault as their own. They felt that their ability to shepherd it toward a solution was lacking in some way, believing that if only their prompts and manually written code were cleaner or more comprehensive, Copilot would surely then be helpful. 6.5.3 Alienation. Alienation is the way Copilot estranges a programmer from their labor and discourages them from interacting with other people. The former includes alienation from the labor process, product, and self, while the latter is social alienation. Labor alienation. Labor alienation was when Copilot disconnected participants from the pleasure and identity they would otherwise find from programming alone, leading their programming labor to feel alien and unfamiliar. For example, participant I-19 describes how their concept of programming as problem solving was corrupted by a singular focus on guiding Copilot. Quote, I had to do less problem solving. It was more solving how to get the right answer out of Copilot rather than get the right answer out of myself, end quote. I-19. More specific forms of labor alienation included feelings of low self-efficacy, lack of satisfaction, and apathy. When Copilot performed better than participants believed they could alone, this caused them to reflect poorly on their own abilities. For example, participant J20 was upset that Copilot could do the same work they could but faster. Quote, I could have probably done this problem, but it did it faster than me. And that's what upset me. Basically, it didn't need me. I'm the dude that puts the stuff in the machine, and the machine does all the work. End quote. J20. Constant reminders of Copilot's proficiency during the study wore on participants. For example, participant I2 ultimately regretted not making more effort to communicate to Copilot, concluding that their initial assumption they might know better was wrong. If I had a do-over, I would, quote, try to leave more comments for GitHub Copilot to understand because I believe it has a better programming sense compared to me, end quote, I2. Once Copilot's effectiveness became clear, failures with it were taken to heart more seriously. Participant I-42 implies that their failure to get unstuck while coding was even more frustrating and embarrassing because they had Copilot's assistance. After accepting their incompetence alone, accepting failure while having an advantage was not as easy. I hate that feeling of being stuck and, quote, I just couldn't continue. And I had this robot helping me and I couldn't continue even with the robot, end quote, I-42. Copilot also robbed participants of the satisfaction of success. Participant I-10 explained that they could take comfort and enjoyment in the knowledge that they can solve a problem alone, which makes coding more fun. For I-43-2, feeling accomplished came from overcoming a challenge without help from Copilot. I'd rather try myself first before using Copilot because, quote, I feel like it's more fun that way. I think it's also I want to know that I can figure it out on my own, end quote, I-10. Quote, I guess it's just a sense of accomplishment when you do it by yourself, end quote, I-43. Finally, 3 participants showed apathy, a lack of care and investment from using the AI. Participant J2 gave up during a solo task because they felt hopeless about being able to succeed without Copilot's help. This sentiment was echoed by J11 when they lost focus at an impasse, saying, quote, parts of me didn't really care anymore, end quote. More concerning was J15's prediction about AI's impact on opinionation in programming. Quote, It will make people less dogmatic about the way they choose to code because they're outsourcing that style, end quote. J15. The point is that when everyone begins using Copilot and other AI code generators, code will begin to follow homogeneous canonical conventions. They expect this to lead individuals to abandon their personal convictions about which approaches are best, since whatever AI produces will be assumed to be best. These different forms of labor alienation indicate that Copilot distances programmers from the enchantment and intellectualism that computing traditionally offered. Users feel pressured to use AI, but then enter their abilities into a contest with it. It is embarrassing to fail with AI, but not gratifying to succeed with it. As a result, some users lose interest in programming because whatever meaning it had to them is missing. Social alienation. Social alienation is when Copilot serves as a substitute for interacting with another person in the programming or educational process. Participants diverged about how AI stacked up to a human alternative. Participants J24 and I4 seemed perfectly fine with taking code and explanations from AI over a human. Talking to Copilot, quote, is the same as asking a teacher, like, quote, hey, I'm stuck. How do I do XYZ? End quote. But you don't have your teacher available, end quote. J24. I don't care whether AI or a human writes the code. Quote, if it works the same, it's the same. If a human can explain it to me, I think I can also try to understand it by myself from the code that the AI produced, end quote. I4. On the other hand, not everyone agreed with settling for the convenience of the AI option. For participant I15, who used the older version of Copilot without the chat function, Copilot's assertive inline suggestions were not comparable to what they would expect from a human. Quote, I'd rather like to talk to someone who can explain why they gave me that solution, rather than here's the solution and I have to, quote, okay, pick it, end quote. I15. Other participants from the I cohort, like I47, also indicated that asking questions about a solution was part of what made human interactions preferable. In the J cohort, participants had access to Copilot chat, so others, such as J2, felt similarly to J24 above. When it is inconvenient to interact with another person, chatting with AI was a suitable substitute. Overall, it seems that AI code generators cause social alienation when they more closely approximate how humans act. Therefore, programmers can expect to become more separated from each other socially as AI and its interfaces continue to improve. 6.5.4 Rationalization. Rationalization is a value system that deems objective, calculable metrics as superior to intangible and subjective experiences. Productivity was the incentivized goal of this study, so using Copilot to be more productive was not relevant here. See pragmatism instead. Rather, quotes reflecting rationalization were those that showed a pre-existing tendency for idolizing technology, seeing efficiency as inherently good, or seeking out optimization of code after it's already being correct. These show ingrained capitalist ideals to glorify technology and numerically explainable perfection. Idolizing technology. Idolizing technology was shown by many participants' overestimations of Copilot's abilities. They often expected Copilot to help them very effectively, reflecting a bias to assume technology is perfect prior to the study experience. Participant I1 found out during the study that Copilot was not as autonomous as they thought. Quote, I was kind of overestimating it, end quote. I was thinking, quote, if I were to just type a few instructions, basic instructions, it'd be able to do the rest for me, which it was not, end quote. I1. Another participant, J13, seemed to think Copilot had not just a good programming sense, but an irrefutable opinions worthy of breaking a tie between misaligned collaborators. They suggested that Copilot would be useful at a hackathon so that a team could move forward with a decision based on its advice. Quote, with a hackathon, you have 24 hours, and you're working with groups of other people. So let's say you and your teammates are having clashing ideas. You can consult Copilot to just see which one it thinks works best, end quote, J13. The assumption that the opinions and actions of AI are superior to those of humans reflects that technology has an image of being deterministic and explainable. Ironically, AI is not in fact deterministic. It borrows the image of older forms of technology, causing a dangerous misperception. While devaluing the non-determinism and uniqueness of humans, this misperception disguises the inhuman randomness of LLMs as a technological ideal. Efficiency. Participants' comments about Copilot's speed indicated that they believed efficiency to be inherently important. For example, participant I-24 thought Copilot would be helpful in completing tedious tasks faster, implying that it is better to complete tasks quickly rather than slowly. This belief explains why other participants often applied an automation bias based on pragmatism. Quote, "It was a lot faster with Copilot than it was without. So I think if you have something you're trying to do, but you have a lot of more tedious things that you need to do in order to accomplish that, I think Copilot would be very helpful." End quote. I-24. Participant I-43 similarly contrasted the popular fear of automation displacing programming jobs to their impression that displacing human workers is worthwhile if it improves the speed of production. AI displacing jobs, quote, "might be good in some ways if it makes things more efficient, but it is usually thought of as a bad thing," end quote. I-43. A mindset of rationalization is so deeply rooted within computing that many readers will trivially concur that efficiency is a worthwhile pursuit. However, other perspectives may consider manual attention to trivial activities and human fulfillment of labor needs to be preferable over efficiency. Somehow, the slowness and tedium of hand-preparing a meal or custom-building furniture does not have an apparent parallel in the writing of computer software. If efficiency is best, then provided AI is fast, automation bias takes over. Optimality. Several participants also placed a value on optimization, going beyond simply wanting code to work correctly toward desiring code which was perfect. For example, unlike those who wanted to produce code itself quickly, participant I2 thought Copilot could improve their learning by teaching them to write code that ran faster when executed. This reflects a desire to have code which is not only functionally correct, but also fast at runtime. Participant I-47 was ambivalent, but also thought Copilot would be useful for writing code that ran more efficiently. Participant J20 most embodied the spirit of optimization, asking Copilot to fix code they already thought was correct. Quote, "Sometimes I would highlight code and be like, /fix the code, even if I didn't have a problem. I just wanted it to look a little bit better." End quote. J20. Along the same lines, participants J13 and I5 mentioned that Copilot could help write more concise code, which they thought was better than longer code that worked the same way. Together, these examples point to a dimension of rationalization that always leaves room for improvement. Users feel they need Copilot's help even when they do not, since they can always make their code better in some way. 6.6 Discussion. The goal of this study was to address the question, how do capitalist values influence novice programmers' relationship to code-generating AI within CS education? Evaluating this relationship requires situating the technology within broader structures that shape it. Code-generating AI does not exist in a vacuum. It is embedded in pre-existing political economic systems that shape its design, use, and the ways learners interact with it. Without such critical analysis, we risk overlooking the potential consequences of its deployment until those consequences have already materialized. 6.6.1 Rationalization and Automation Bias. We found that novices' values reflected capitalist trends of rationalization and reverence for technology that triggered self-reinforcing automation bias. In capitalist economies, the logic of private accumulation encourages individuals to pursue self-interested actions that ultimately serve economic gain. As Weber argued, such preferences for outcomes that maximize material efficiency become standardized through bureaucratic systems. Once systematized to generate predictable revenue streams, these practices not only become the norm, but are valued above alternatives that emphasize autonomy or creativity, because they so reliably deliver the economic returns embedded in the political economy. From a sociological perspective, this is the hallmark of rationalization. Human action comes to be governed by calculability and efficiency rather than values of intrinsic meaning. In this context, technologies like Copilot are not tools but embodiments of rationalized systems. Participants' immediate framing of Copilot as pragmatically useful reflects this preference and demonstrates the hold of instrumental rationality on novice programmers, who expressed a desire to simply complete the task. For many, it mattered little how the task was achieved so long as it was completed, underpinned by the assumption that task completion itself carries inherent value. Here, we see how the commodity form shapes educational labor. The exchange value of finishing a task, grade, credential, or performance metric overrides the use value of programming as a learning process. The very structure of education under capitalism normalizes this substitution, positioning students to see efficiency itself as the end goal rather than knowledge, autonomy, or skill development. This phenomenon operates in two directions. While the political economy produces a preference for efficient outcomes, it also shapes the standards of computing labor that novices internalize as they prepare for future work. Participants frequently acknowledge that relying on Copilot might hinder their learning, since it performed the coding for them. Yet many coupled this recognition with the claim that such drawbacks mattered less for the, quote, real world, end quote, where the labor market values speed and output over critical engagement or creative ingenuity. These dynamics reveal how students are positioned simultaneously as consumers and producers within CS education. As consumers, they adopt AI tools like Copilot that are marketed on promises of efficiency, personalization, and convenience. Yet as producers, their labor, assignments, skills, and ultimately credentials functions as capital that universities and employers commodify. Copilot collapses these roles. Students consume automation while producing outputs that are valued less for their intrinsic meaning than for their exchange value within educational and labor markets. A prior qualitative study found that software engineers using neural machine translation subscribed to this idea, believing a working product mattered more than whether AI produced the code. Our participants echoed this logic. They emphasized the importance of efficiency and expressed a desire for code that approached optimality, defined in terms of runtime speed, aesthetics, and conciseness. Notably, some framed this pursuit of optimality through an uncritical trust in AI, treating it as an infallible source of expertise capable of delivering such outcomes. This tendency signaled a pre-existing inclination of idolizing technology. Several participants even spoke of Copilot in human-like terms, elevating its outputs as the ideal choices. Such responses illustrate how prevailing market values shape conceptions of AI. Technology becomes revered under the sway of instrumental rationality, precisely because of its perceived ability to achieve economic ends with efficiency. Placing Copilot onto a pedestal predisposed participants to apply an automation bias in their interactions with it. While novelty may have played a role, as suggested by prior aid studies, participants largely cited pragmatic reasons for relying on the tool. Pragmatism drove them to have Copilot take over and produce code for them, as it was very effective at doing so. Many believed Copilot to be effective, and under conditions where they were incentivized to perform highly and allowed to use AI as much or as little as they wished, they often delegated tasks to it. This is not direct evidence of over-reliance, but it does reveal how capitalist priorities, productivity, and efficiency shaped their responses. Participants frequently used Copilot even when they did not need to, indicating that when speed was paramount, automation became the preferred strategy. In a world where efficiency is equated with quality, it is unsurprising that participants came to idolize technology, especially the performative capabilities of Copilot. This tendency cannot be dismissed as an artifact of experimental design. Prior studies have found similar patterns. Participants requested full solutions from AI code generators, accepted clearly flawed code, and used outputs in ways that revealed limited understanding. Ritzer's theory of McDonaldization, an extension of Weber's rationalization, helps explain this trend. All sectors of life, he argues, have come to prize efficiency, predictability, and control. Copilot embodies these logics. It delivers speedy, reliable outputs that reduce uncertainty while also manifesting the fourth tenet of McDonaldization, control through non-human technology. In rationalized systems, people are viewed as the greatest sources of inefficiency. From this perspective, companies adopt AI to reduce error and increase control, while students, as seen in our study, apply automation bias because they believe delegating to AI maximizes accuracy and minimizes mistakes in their own interest. Though this deference occurred in an experimental context, it likely reflects the attitudes novice programmers will carry into the labor market, where automation is prized for completing tasks quickly, reliably, and with minimal human error. As with our participants, their bias manifested as passivity within the interaction. They let Copilot take over control and, like in reference 83, sacrificed understanding and entered unrecoverable cycles of debugging. While this was sometimes initiated by voluntary actions, Copilot's triggerless suggestions also caused involuntary passivity. By seeing its suggestions before having a chance to think, users are biased by what they see and forced into a passive role. This is similar to the ideas of, quote, incidental specification, end quote, discussed in reference 31, and Copilot's intrusion on novices' thought processes reported in references 59 and 58. Rather than users having the agency to make requests of AI, triggerless suggestions encourage prompts which are crafted as an unintentional byproduct of the coding process and interruptions which can be distracting and persuasive. The influence of AI also leaves a lasting mark. When participants went back to programming alone, they suffered the constant temptation to use Copilot instead. Knowing what it had to offer them, it was hard to shake the thought that any difficulties they encountered were unnecessary and avoidable. The tempting nature of Copilot's suggestions for novices was reported in reference 59, but several other studies further explain the impact. One study of CS1 students found that participants in a group with access to ChatGPT underutilized course materials, internet search, and peer forums compared to those in the control group. Similarly, 2 prior studies found that CS students' use of AI code generators was bimodal, either using it heavily or very little at all. Together, these and our findings suggest that aids create a black hole effect, where students are lured in by benefits that they then struggle to leave behind. Finding 1. Novice programmers have pre-existing values to favor programming goals that can be calculated numerically, tending also to favor technology to achieve these. By discovering GitHub Copilot's effectiveness for enhancing productivity, participants applied a bias for using AI that reduced autonomy and embedded a reinforcing temptation to do so repeatedly. 6.6.2 Individualism. We also found that novice programmers' belief about the responsibility of an aid user reflect individualistic capitalist values. In a capitalist economic system, an individual is expected to gain and lose capital according to their own choices. A neoliberal ideal would suggest that responsible decisions, those that produce valuable software with minimal negative externalities, are incentivized by a free market. Irresponsible decisions, such as those compromising safety by deprioritizing quality control, should then, theoretically, be punished by consumers choosing other producers in the market or civil lawsuits that incur economic penalties. Aids like GitHub Copilot can produce code with security vulnerabilities, and this can lead programmers to write less secure code when using an aid. Though AI is ostensibly to blame for such an impact on code quality, individualism reflects a tendency to blame the human user instead. This echoes neoliberal logics of responsibilization, where systemic risks and responsibility shift from higher institutions to the individual, who must continually manage their own exposure to failure. This was reflected by our participants' ascription of responsibility to themselves through the entire process of using Copilot. First, they felt they should apply self-regulation to decide whether using Copilot was appropriate at all, and then for deciding how much to use it. In neoliberal systems, self-regulation is not only a pragmatic skill, but also a moral obligation. Subjects are expected to internalize discipline and treat their own behavior as a site of investment. This illustrated what Marx would describe as alienation, shifting of responsibility for structural conditions onto the laborer, even when the means of production introduce risks outside the worker's control. CS education researchers agree that students will need to self-monitor and self-regulate, but also emphasize the need for better metacognitive support to enhance the effectiveness of aids for meeting learning objectives rather than productivity objectives. A study of CS students measured subjective self-regulation and self-reports of AI use, finding no relationship. This indicates that though it is easy to expect students to regulate their use of AI, it may be that the design of aid interfaces is influencing them to use it ineffectively for learning. Participants also felt they were responsible for shepherding, understanding the task at hand and communicating it well to Copilot. Beyond the formalization of shepherding as an interaction pattern by Prather et al., several prior studies have noted the importance of an aid's user taking on this role. What is less often expressed is a responsibility of the aid or its producer to effectively obtain the necessary information from the user. An example of this perspective is the Kiro IDE, which uses AI in a specification-driven development paradigm that takes concrete steps to request the user's intentions before generating content. The expectation for a user to guide and control the aid instead is an ironic one given AI's tendency to degrade user autonomy. This expectation can be seen as part of rationalization, where tools designed to make work more efficient actually embed new procedural demands onto workers, narrowing their autonomy further. Individuals paradoxically bear heightened responsibility for outcomes even as actual decision-making authority shifts toward automated systems. However, in a neoliberal mindset, the AI creator has produced value by creating the aid, so the user is expected to take over responsibility by learning to use and adapt to it from there. The final responsibility participants felt was one for taking ownership of the code itself and a knowledge about how it worked. This reflects Braverman's analysis of de-skilling. While technology simplifies some tasks, the worker is simultaneously burdened with accountability for the labor process they no longer fully control. A prior social media study noted that AI use by inexperienced programmers was deemed unacceptable in safety-critical domains since the programmer must remain accountable for code reliability. The extension of accountability for understanding of produced code was also reflected by the perspectives of CS students reported in Reference 91. Several participants conveyed negative judgments about the idea of students using code from generative AI without being able to explain how or why that code was appropriate. Here again, capitalist individualism shows through, as code is considered a product that reflects implicit promises from the programmer. This baseline expectation motivates many software producers to deliver their code with licensing documents, for example, the MIT license, that explicitly disclaim responsibility for any issues a user may encounter with the software. In Marxist terms, this resembles the commodification of intellectual labor. The code is abstracted into a commodity that can be exchanged, while the liability is pushed away from producers onto individual users. Certainly, in CS education, the assumption of full understanding being necessary should be scrutinized. In the past, understanding code fully was unavoidable for an effective programmer, but the capabilities of aids potentially change this fact. If an explanation of code is truly needed for some maintenance or auditing purpose in the future, perhaps another AI-based tool could take on the task. In such a case, a student could be successful by producing useful code even without understanding it. Considering code as a form of capital accrued by the programmer's labor perpetuates the idea that they should be held accountable for its every consequence. Instead, if code is merely a means for computers to communicate human values to one another, only the values originated by humans might be scrutinized. Individualism also caused guilt and self-blaming for our participants because of the broad responsibilities they placed on themselves. Not only did participants feel they should self-regulate their AI usage and own an understanding of the code, they also felt it was morally wrong not to do so. This aligns with concerns reported by students and educators in prior work about AI's likelihood of contributing to academic integrity violations. At the same time, CS educators recognize that the purpose of CS education may be changing as AI is adopted in industry. The rational obsession of capitalism with quantifiable productivity metrics will drive the adoption of aids, reducing the need for programmers to know how to code manually. This means that our participants' feelings of guilt may be misplaced, causing unnecessary harm to them. This resembles a neoliberal subjective account, where individuals come to govern themselves through guilt when they cannot live up to market logics of productivity and accountability. This also mirrors the critique of education under neoliberalism. Students are increasingly treated as entrepreneurial actors responsible for optimizing their own learning, even if structural conditions limit their agency. Participants also blame themselves when AI did not help them effectively, pointing to their failure to understand and guide Copilot as the root problem. Though many prior studies recognized the importance of the user's behavior, they did not all report such an effect on users' feelings. Users may not have blamed themselves directly, but they also avoided blaming the AI. However, when time pressure was imposed as we did here, participants did blame themselves. Some participants, in reference 59, also saw no downside to using Copilot when they used it without any time pressure. The takeaway is that performance-centric environments, which exist for educational assessments and time-bound projects, encourage aid users to blame themselves for productivity issues. Finding 2. Novice programmers have individualistic mindsets that make them feel immense responsibility for using AI appropriately at every stage. They feel guilty for handing over control to AI, lose satisfaction when succeeding with it, and blame themselves when failing with it. 6.6.3 Alienation. We also found that Copilot alienated participants from the programming process and threatened their interest in future social activities. By fulfilling programming work, Copilot takes control away from the user. Early work found that some programmers are averse to this process, desiring to maintain control of the interaction. This is also unsurprising given the burdens users place on themselves. See section 6.6.2. They cannot afford to give up control if they are liable for the consequences. As they let Copilot do more work, they lost touch with their own sense of value within the programming process, acting merely as users rather than creators. This resonates with Marx's theory of alienation, in which workers become estranged from the product of their labor, from the process of production, from themselves, and from other workers. Copilot's intervention simultaneously detaches students from the code itself, from the act of coding, and from the collaborative relationships that programming education often relies on. This was also reported in an early qualitative aid study, where programmers changed their commenting behaviors to adjust to Copilot. Their participants were palpably enthusiastic about their changing role, but the tone from ours was one of disillusionment with Copilot and its growing abilities. They felt apathy toward challenging problems and advocating for their opinions, and described how producing correct code was less satisfying with Copilot than doing so alone. Here we see what Braverman calls, quote, de-skilling. The automation of complex labor reduces the worker to a monitor of the machine rather than an active problem solver, hollowing out opportunities for creativity and satisfaction. Whereas in human pair programming, students' feelings of satisfaction increase, collaborating with AI is alienating. The comparison between AI and human partners also echoes the concept of rationalization. Efficiency and predictability replace social bonds, with technical success prioritized over human meaning-making. A related challenge is the blurring of lines between AI and other tools, which prior work has reported as a challenge for novices. If students may not even be sure whether they used AI to complete a task, their self-reflections may be harder to place. Anecdotally, we noticed some participants confusing the automated testing interface as being part of Copilot's functionality. Overall, though, they seemed to know when they were using Copilot. Seeing how effective it was, participants compared themselves to Copilot disfavorably, harming their self-efficacy. This goes against prior work that suggests aids can improve student self-efficacy, aligning better with evidence that AI use correlates with low self-efficacy. It may not be that AI simply increases or decreases self-efficacy directly, but instead that it provides novel avenues for either change to occur. Here, we see that comparison is a clear avenue for self-efficacy harm. In CPE terms, this illustrates how capitalist competition structures identity. Students measure their worth against the productivity of a machine, internalizing market logics that position them as failing entrepreneurs of their own labor power. Students tie their sense of purpose and self-worth to productivity rather than craft or skill. If students fail to complete a task, they see themselves as bad coders. If they succeed on the task with Copilot, their sense of skill is undermined because the accomplishment belongs more to the tool than to them. This creates a lose-lose situation where failure feels personal and success diminishes their sense of identity as programmers. The broader implication is that the human role in coding is shrinking. Students start comparing themselves to AI, which they view as faster and more effective, and conclude that they can't compete in a society obsessed with efficiency. Finally, we noticed trends in participants' comments that placed Copilot as a threat to social interactions with peers and instructors. We found mixed opinions about whether Copilot could replace a human interaction, but hesitancy seemed to be around perceived limitations of Copilot's features. Due to the rapid pace of advancement, participants at our 2 study sites used different versions of Copilot, with the second group having a chat feature available. It seemed that for participants who could get explanations from Copilot, the need for a human who could do the same was less necessary than for those participants who had only in-editor suggestions. Specifically, the ability for aides to explain things in natural language has been an essential feature for user acceptance in prior studies of both students and professionals. Limitations that have been reported by participants in the past are also steadily becoming commonplace among aids like Copilot. For example, the introduction of agent behaviors to Copilot has enabled it to ingest outside resources for use in the programming context, something that users previously cited as a limitation. Many studies have reported the tendency for users to anthropomorphize aids, and this stands only to continue as feature sets expand into tasks previously considered as inherently irreplaceable. Whereas reference 31 suggested participants may have distrusted AI-generated code as compared to that written by instructors, our participants did not seem to think so. Peer and instructor relationships lose value unless they can provide a comparative advantage over automation. Therefore, the affective and social dimensions of education risk being hollowed out, valued only insofar as they enhance efficiency. We argue that their sentiment originates from the structure of a capitalist economy. Labor is the origination of capital itself, so accumulating capital depends on human labor. Rather than considering the interaction among humans as valuable within itself, the capitalist framing says that human interactions are only valuable to the extent they outperform the alternative to use automation. Finding 3. AI exacerbates capitalism's alienation of programmers from labor and human relationships because it diminishes the traditional humanity of writing and understanding code. 6.7. Educational implications and recommendations. To counteract the harms of code-generating AI, CS education should respond by encouraging students to challenge their own assumptions about what goals they have for programming endeavors. Overall, we consider the goal of computer science to be using computers to promote human welfare. Our findings show that capitalist values pervade CS students' perspectives about programming and using AI code generators. We observed patterns of rationalization and automation bias by which participants prioritized productivity and perfection, preferring an aid for achieving these over programming alone. Resulting harms were that participants felt guilty for using GitHub Copilot, inadequate in comparison to it, and responsible for negative outcomes but not positive ones. They felt alienated from programming and revealed ways Copilot will threaten social relationships by assuming a pseudo-social role. If CS students apply a mindset to use AI in pursuit of calculable goals, they may promote human welfare in parallel to capital accumulation. However, by engaging with opposing perspectives, students can form more nuanced and holistic approaches to using AI in their computing education and careers. Next, we propose intentionally contrarian perspectives to our findings. We define these not to claim they are correct or superior to capitalist ideals, but merely to give educators a concrete Socratic basis for challenging vague and latent assumptions. Each of these perspectives can be applied in non-technical instruction, an important but often overlooked aspect of programming education. 6.7.1. Challenge rationalization. Participants were unsurprisingly influenced by a dominant value to glorify coding quickly to produce fast-running optimal solutions to problems. While at first, this seems apparently in line with a goal to promote human welfare, the perspective is myopic to the relative importance of perfection in a given context. There are many cases where metrics for productivity fail to correlate to true value to humanity. Marx emphasizes that capitalism promotes the exchange value of a product rather than its true use value. As an example, developers in a corporate setting might be encouraged to work through project management tickets quickly as a measure of productivity. If a developer works on a valuable task that is time-consuming but only completes a single ticket, the ticket speed metric could give an inappropriately poor representation of their contributions, even in an economic sense. Whereas the exchange value of the work to clients might be low in that ticket resolution time would be high, the use value to the client might still be high given that the developer made an important contribution. This concept extends to investments by students in time-consuming educational programming. As our participants discovered, programming with Copilot gave a clear performance advantage while working under time pressure. However, the presumably lower engagement with the work they complete with AI can lead to poor representation of the endeavor's success. Perhaps some concept learned in a slow solo programming experience as a student can translate several years later to the programmer developing a life-saving advancement to the firmware in a medical device. In the short term, it seems that the student has covered the same material in a longer time period, making working slower worse. In reality, the investment of time as a student is clearly valuable when considered at a systems level. 6.7.2. Promote communal perspectives. Participants felt they had responsibility as users of code-generating AI for how much to use it, how to use it, the code resulting, and the consequences of that code. Notably, neither the vendors of user-facing AI products nor the maintainers of back-end AI infrastructure were discussed in this chain of responsibility. Whereas capitalist individualism leaves a CS student liable for their behavior in relation to AIDS, a communal perspective cautions other actors in the society to avoid behaviors that set users up for failure. For example, GitHub Copilot's student discount gives CS students an opportunity to use a premium aid for free. This has the benefit to help students learn about AIDS and gain any learning benefits, but can also harmfully broaden the reach of the alienation we identified. Furthermore, the design of aids has productivity in mind, though certain features such as system prompts or, quote, instructions, as they are named within Copilot's interface, may be useful for CS students to better align their desire to learn to an aid's behavior. Vendors do not take responsibility for encouraging users to take advantage of such features. Discussion with students on these topics will be important as they transition from AI consumers to AI producers. Education that considers broader purposes for using aids can then incite later generations of the technology to represent additional values beyond only capitalist ones. 6.7.3. Emphasize developer experience. Copilot's positioning to alienate CS students from themselves, the labor of programming, and their social connections represents a deprioritization of their developer experience, DX. Though human-centered computing often promotes human welfare by upholding user experience, UX, it sometimes fails to consider the importance of DX. Just as burnout and dissatisfaction of medical professionals can be harmful to the patients their labor supports, dissatisfied programmers are impaired with respect to creating value for humanity. Additionally, finding purpose and self-efficacy within programming is a vital prerequisite for students to persist through education to the point of being strong contributors later on. As such, it is vital that educators stress to students that they deserve to find enjoyment, satisfaction, confidence, and social connections within their work, even if it costs time. Accessing useful aids is becoming easier by the year, such that the time and effort associated with solving a problem alone or traveling to an instructor's office space to take a face-to-face meeting seem impractical. Students must be taught to hold simultaneously that using AI can enhance their programming, but prioritizing themselves as humans is an upstanding trade-off. This means they should take license to work together with peers over AI, accept worse code that they are proud to have produced without AI, and treasure inefficiently gained knowledge for its unrealized future benefits. 6.8. Threats to validity. Our study design may be considered a contrived scenario in that participants were encouraged to be as productive as possible with an AI assistant known to be performant on the tasks they completed. This would tend to amplify apparent automation bias and worsen alienation and negative individualistic thought patterns. Still, our results expressed capitalist ideals beyond what the study design alone could explain. Regarding generalizability of the study tasks, we note that programmers may find more active participation, meaning, and self-efficacy within complex real-world problems for which AI is less helpful. This would reduce reliance on AI and associated feelings of guilt too. However, as AI improves, the exaggerated experiences we captured will likely transfer to increasingly difficult problem spaces as the practical need for human involvement decreases. This study is not highly generalizable to non-US economies. Although globalization promotes US economic values across the world, and several of our participants had non-US national origins. The results are most applicable to the post-secondary educational culture at public universities in the eastern US. As for the validity of our method, we acknowledge our subjective lens but maintain that our systematic multi-rater process delivered an honest representation of our participants' experiences. We made efforts to represent as many of the participants' voices as possible and capture the breadth of their experiences. While our findings provide little direct evidence regarding how capitalist values and aids interact to harm CS students' learning, we encourage future work to explore how the hazards we identify may be counterproductive to the mission of CS education. 6.9. Conclusion. This study used Marxist and Weberian theories to identify the harms of AI code generators to students within the market-driven CS education pipeline of the United States. We identified 3 key findings. 1. Measurable programming goals were prioritized, with a preference for using AI to achieve them. 2. Programmers were considered personally responsible for every aspect of programming with AI. 3. Code-generating AI alienates programmers from their labor and their social connections. We recommend that CS education trains students to be AI literate rather than AI dependent by exploring pedagogies that critically and strategically integrate AI. This involves not promoting, but merely presenting counter-capitalist ideology into non-technical dialogues within CS classrooms.